will continue our discussions on the displacement analysis of robots. So, we have looked at 2 degree of freedom manipulators. Today, we are going to look at a 3 degree of freedom parallel robot manipulator, open chain manipulator. So, this is the overview of today's lecture. So, the displacement analysis problem, forward and inverse kinematics of a 3R open chain planar manipulator. So, as we have discussed, our plan, we are discussing planar robots with open chain. Subsequently, we will discuss planar robots with closed chain configurations. So, we have already defined this forward and inverse kinematics problem. So, there are 2 problems in displacement analysis. So, given the actuator input, to find out the output motion of the end effector, and the inverse kinematics problem is for a specified output of the end effector, that means specified position and possibly orientation of the end effector, we have to find out the actuator inputs. So, inputs are the actuator displacements and the output is the end effector position and orientation. So, now we are going to look at this 3 degree of freedom kinematic chain, a 3R planar open chain manipulator. So, this is a schematic of a 3R planar open chain manipulator, and here I have written out for you the forward kinematics problem. So, given these angles theta 1, theta 2 and theta 3, we have to find out the location of the end effector. So, x e and y e. Since this is a 3 degree of freedom manipulator, so we can have 3 variables at our control. So, this x e and y e and this orientation angle phi. So, given theta 1, theta 2, theta 3, the forward kinematics problem is to find out x e, y e and phi. So, x e, y e, these are the locational coordinates of the end effector, and phi is the orientation of the orientation angle of the end effector. So, here we have 3 revolute pairs. And we have to now find this relation. So, here is the schematic once again. So, what do you have to do? We need to locate this coordinates of the end effector in terms of theta 1, theta 2 and theta 3. So, coordinates of the end effector, so this is the x e. I can write that this x e is the summation of the projections of the 3 link lengths on the x axis, that will give me x e. So, therefore, x e I can write as projections of the link lengths, summation of the projections of the link lengths on the x axis. So, the projection of link length L 1 is L 1 cosine theta 1. very easy to see. That is the projection of L 1. So, C theta 1 stands for cosine theta 1. Similarly, the projection of L 2 I have to add to this. Now, what is the projection? So, if I draw a line parallel to the x axis, so cosine of this full angle. Now, this full angle is, this is theta 1, remember. So, theta 1 and this is theta 2. So, theta 1 plus theta 2. So, L times cosine theta 1 plus theta 2. So, that gives me the projection of link length 2, link length L 2 on the x axis. Similarly, the projection of link L 3 once again. So, this is a line parallel to the x axis. So, projection of L 3 on the x axis will be L 3 cosine of this whole angle. Now, this whole angle is composed of the following parts. This angle, is same as this angle, as you can see. So, this is theta 1 plus theta 2. So, therefore, the whole angle that L 3 makes with the x axis is theta 1 plus theta 2 plus theta 3. So, therefore, I must add this projection as L 3 cosine of theta 1 plus theta 2 plus theta 3. So, that completes the x coordinate of the end effector. Similarly, I can write the y coordinate as the projection of these link lengths on the y axis. So, to start with, this is the projection of this distance is the projection of L 1 on the y axis, and this can be written as L 1 sin theta 1. So, therefore, the first term here is L 1 sin theta 1 plus. Now, the projection of L 2 on the y axis, so is nothing but L 2 sine of this whole angle, and this whole angle is nothing but theta 1 plus theta 2. So, L 2 sine of theta 1 plus theta 2. Similarly, the projection of L 3 on the y axis is L 3 sine of this whole angle. Now, that whole angle is theta 1 plus theta 2 plus theta 3, as we have noted. So, this becomes L 3 sine of theta 1 plus theta 2 plus theta 3. So, that completes the y e locational coordinate of the end effector. What remains is the orientation angle phi. Now, you can very easily see that this full angle same as this angle phi. So, therefore, I can write phi as theta 1 plus theta 2 plus theta 3. So, that completes the forward kinematics problem of this 3R planar open chain manipulator. So, I will show this to you formally. So, this is the end effector positional coordinates x e and y e, and we have the orientation coordinate phi as theta 1 plus theta 2 plus theta 3. Now, the inverse kinematics problem. Once again we have these angles theta 1, theta 2, theta 3, which are now unknown, but what is known is the location of the end effector, that means x e and y e, and the orientation of the end effector phi. So, these are the three quantities which are specified, and what we have to find out are these joint angles theta 1, theta 2 and theta 3. So, we will start with the forward kinematics expressions. So, the relation between x e y e phi and theta 1, theta 2, theta 3. Then we note that you see this phi, this appears here and here in the locational coordinates of the end effector. So, therefore, I can replace these by phi. Which is specified. So, remember these quantities are specified. So, phi is known to me. Now, once I substitute this theta 1 plus theta 2 plus theta 3 by phi, this term, the third term, is completely known to me. So, I can bring it to the left hand side and write so, from the first equation and similarly from the second equation. Now, once I have these two equations, the left hand side, remember, is completely known to me. I call them capital X and capital Y. So, capital X and capital Y are completely known because x c and phi are known to me. So, the problem now boils down to finding out theta 1 and theta 2 given capital X and capital Y. So, the simplest approach would be to look at this x minus L 1 cosine theta 1 whole square plus y minus L 1 sin theta 1 whole square. So, I have taken this term to the left, this term to the left in the two equations, squared them up and added them. So, I get on the right hand side L 2 square. So, when I open this up, I get x square plus y square plus L1 square minus 2 L1 x cosine theta 1 minus 2 L1 y sin theta 1 is equal to L2 square. So, I can now manipulate this and rewrite in this form: y sin theta 1 plus x cos theta 1 is equal to x square plus y square plus L1 square minus L2 square divided by 2 L1. So, I have re-expressed this equation in this form. So, this form again is familiar: a sin theta 1 plus b cosine theta 1 equal to c. So, you can find the correspondence: a is y, b is x, and c is this expression on the right hand side. So, let us look at these steps formally. So, I had this definitions of capital X and capital Y. Now, these capital X, capital Y in terms of theta 1 and theta 2. So, I took these terms on the left hand side, squared them, added and expressed this, which can be reframed in this form: a sin theta 1 plus b cosine theta 1 is equal to c, where this a, b and c we have seen how to derive. So, we know a, b and c because this x and y are known to us: x e phi, y e phi. So, these are all known to us. So, capital X, capital Y are known, therefore, a and b unknown. So, we are left with the only unknown theta 1 in this equation, which we can solve. So, that will give us the solution of theta 1. What about theta 2? So, theta 2 you can see that if I take these terms to the left hand side and take the ratio of the second equation with the first, then I have tangent of theta 1 plus theta 2 is equal to y minus L1 sin theta 1 by x minus L1 cosine theta 1. So, I have taken these terms to the left hand side and taken the ratio, the second equation with the first, and I have this. Now, from here I will first solve for theta 1, then substitute this theta 1 solution of theta 1 into this and solve for theta 2. So, we are going to look at this step by step. So, first we are going to look at this equation. So, solution of A sin theta 1 plus B cosine theta 1 equal to C. Once again we make this definition, so that we express sin theta 1 and cosine theta 1 in this form in terms of x. These expressions when substituted into the master equation results in this quadratic equation in x, which we know how to solve. So, the solutions are given by this expression, and x is tan theta 1 by 2. So, I know how to find out theta 1. Here A, B and C are completely known. So, we will know x and hence tan theta 1, and finally we have the solution of theta 1. Once we have the solution of theta 1, as we have discussed, we found this expression. So, theta 1 is completely solved. There are two solutions. So, therefore, I know theta 1. So, there are three places we need to substitute and take the tangent inverse and get theta 2. Once I solve for theta 2, so I have theta 1 and theta 2, then I can solve for theta 3, because phi is known. So, that will complete the solution. And once again, when you take tangent inverse here or in the previous step, we must use the A tan 2 function. So, here is the complete solution in one go. So, we have these two solutions of theta 1. Correspondingly, we will find the solution of theta 2 from here, and finally theta 3. So, once again we use this A tan 2 function when we solve these things on the computer. So, let us now understand the solution graphically. Here remember that x e, y e and phi, these are specified. Once these three things are specified, this link gets completely fixed. This gets completely fixed. Because one point is fixed and the angle is fixed. So, this link is fixed completely. Therefore, this point is completely fixed. This revolute joint is completely fixed. What is not known is theta 1 and theta 2. So, therefore, this is fixed. I can then rotate L2, the link L2, about this fixed point, and similarly L1 can be rotated about this fixed point to find out where this hinge lies. So, this is the circle on which this hinge on L2 moves, and this is the circle on which the hinge on link 1 moves. Therefore, the intersection points are the possible solutions. So, one solution is given in this black configuration. Let me draw the other configuration, other possible solution in blue. So, this here is the revolute pair, the hinge, and in the blue configuration also this link remains fixed, this is fixed. So, one is the black configuration, the other is the blue configuration. So, these are the two solutions of the inverse kinematics problem. Next, we look at the workspace. If all the revolute pairs can rotate completely, then we find that this revolute pair can go on this circle, this revolute pair can move on this circle, and the end effector can rotate. So, these are the three revolute pairs. So, the farthest reach is when the manipulator is completely extended like this, that is the farthest reach. And by rotating this completely, I can generate the boundary of the reach of the manipulator. On the inward side, this can be folded I can reach any point like this. I can reach points like this. So, I can cover the complete space within the outer circle. So, I can reach any point in this region. So, for a 3R manipulator, all points can be reached. You can, so that of course will depend on these link lengths. So, these link lengths L1, L2, L3, the way I have drawn you can reach, but if L2 and L3 are short, then there might be some regions that are left out. So, that is the workspace for the 3R manipulator. There is another restriction, that is on the joint angles. If they have limits, then also the workspace gets restricted or reduced. So, here is a summary. So, we have looked at the 3R open chain manipulator, looked at its forward and inverse kinematics, and we have discussed the geometric interpretation of the solutions of the inverse kinematics problem. So, with that I will close this lecture.